Let's travel back in time for a second. Imagine it's the late 1890s. Physics, for pretty much everyone, feels, well, finished. You've got this incredible structure, classical mechanics, thermodynamics, electromagnetism, and it all just seems to be this beautiful, complete, and pretty much perfect description of how the universe works. It really felt like all the big ideas had already been figured out. And this quote, man, it just perfectly captures that vibe. The core theories from geniuses like Newton and Maxwell were basically considered settled law. The universe was seen as this giant, predictable clockwork machine. All that was left to do, it seemed, was to just sharpen our measurements. Check that next decimal place. But as we're about to see, hiding in those few minor problems were the seeds of a revolution that was about to blow the whole thing wide open. I mean, this classical world was built on these magnificent pillars, right? You had Newton's laws of motion, Maxwell's equations that magically tied together electricity, magnetism, and light, and of course, the laws of thermodynamics. It was an absolute masterpiece of science that worked for everything from planets orbiting the sun to steam engines. The job, it really seemed, was done. But this is where that beautiful, complete picture starts to, well, unravel. A few stubborn, nagging experimental results just wouldn't fit, no matter how hard the best minds in physics tried to make them. The first really big crack in the foundation came in 1897. A physicist named J.J. Thomson, playing around with a cathode ray tube, proved that atoms were not the fundamental, indivisible building blocks everyone thought they were. He discovered a particle inside the atom, the electron. And bam, just like that, the atom had internal parts, a complexity that classical physics was totally unprepared to deal with. Okay, now this is where classical physics didn't just fail, it failed spectacularly. The problem was something called black body radiation, basically the light that a hot object gives off. The existing theory, that's the dashed red line you see, predicted that as you get to higher frequencies, like ultraviolet light, the amount of energy it emits should shoot off to infinity, literally infinite energy. It was so absurdly, comically wrong, they gave it this awesome name, the ultraviolet catastrophe. And you can see why. The real data, those solid curves, showed something completely different. So how do you fix a catastrophe? Well, the solution came from Max Planck in 1900. In what he later called an act of desperation, he just tinkered with the math. He introduced a new number into physics, a constant, h, and suggested that maybe energy isn't emitted smoothly, but in little chunks, or quanta. It was just a mathematical trick, a fudge factor that happened to make the theory line up perfectly with the real-world data. He had absolutely no idea why it worked, just that it did. So, Planck's weird little idea is out there, kind of floating around. But the next clue was about to take it from being just a math curiosity and turn it into a physical reality. This time, the mystery was all about what happens when light hits a metal surface. It's called the photoelectric effect. And this slide just lays out the train wreck perfectly. Classical wave theory made two very clear predictions. One, brighter light should knock out electrons with more energy. Two, even a really dim light should work eventually if you just shine it long enough. But what actually happened in experiments? The complete opposite. The electron's energy had nothing to do with the light's brightness. It only depended on its color, its frequency. And if the frequency was too low, nothing happened at all. You could shine the brightest light in the universe on it, and not a single electron would budge. The classical model wasn't just off by a bit. It was wrong about, well, everything. And then, in 1905, a young patent clerk you may have heard of, Albert Einstein, took Planck's desperate act and made this absolutely staggering leap. He said, what if this whole quanta thing isn't just about how energy gets emitted? What if it's what light is? He argued that light actually travels as little bullets of energy, which we now call photons. And each photon carries a specific amount of energy, Planck's constant, times its frequency. E equals h nu. And the proof? Oh, the proof was just undeniable. This graph is the smoking gun. If you plot the kinetic energy of the electrons that get knocked out against the frequency of the light you're using, you get a perfect straight line. And the slope of that line? It's none other than Planck's constant. This was just this stunning confirmation. Einstein's photon idea perfectly explained every weird thing about the photoelectric effect. So we've got quantized energy emission and we've got quantized light itself. But the third and maybe the strangest clue of them all came from looking at the light given off by superheated atoms. And this final mystery would tell us something profound about the very nature of matter. You see, when you pass the light from a heated gas through a prism, you don't get a smooth, continuous rainbow like you do with sunlight. What you get instead is a series of sharp, separate lines of color, a unique atomic barcode for every single element. So the huge question became, why? Why do atoms only spit out light at these very specific, isolated frequencies? What did this barcode even mean? This became the central question. For years and years, scientists would just stare at these lines, trying to find some hidden pattern, some mathematical key that could finally unlock the secret of the atom. The first breakthrough came from a really unlikely source. In 1885, a Swiss schoolteacher named Johann Balmer found this surprisingly simple formula that perfectly predicted the frequencies of the hydrogen lines you can see with your eye. But it had this super weird feature. It only worked if you plugged in whole numbers for the variable n, 3, 4, 5, and so on. Integers. What in the world did simple integers have to do with an atom spitting out light? Well, this was soon generalized into the Rydberg formula, and all of a sudden, the frequency of every single line in the entire hydrogen spectrum could be calculated from this one beautiful equation. And just look at it. As the quote says, the fact that this whole thing is controlled by the difference between two simple integers is truly amazing. Simple whole numbers were dictating a fundamental process of nature. It was mind-boggling. So now we have our three major clues, right? The failure of blackbody radiation, the strangeness of the photoelectric effect, and this mysterious integer-based pattern of atomic light. Three seemingly separate problems that were all pointing to the exact same mind-bending conclusion. And here it is, the grand unification. All of these mysteries were just different faces of the same fundamental truth. At the smallest scales, energy is not continuous. It's discrete. It comes in packets. It comes in quanta. The universe is granular. The smooth, continuous world of classical physics was just an illusion, a really good approximation that completely breaks down when you get to the atomic realm. The quantum era had officially begun. Which brings us right here to this final question. The greatest revolution in the history of physics was born from anomalies that were at first dismissed as just minor details. It really forces you to wonder, doesn't it? What are the ultraviolet catastrophes of today? What are the tiny experimental glitches we're seeing right now, maybe in dark matter or in quantum gravity, that might just be the first hints of a completely new and maybe even stranger reality?